be sure to make sure that the plug is plugged in. Okay, I feel like you folks have felt like you've had enough, but I'm sorry, there's more. Okay. Can I just pause to say, are there any questions? What have we learned? We have learned a formalism, a formalism. There are other formalisms, but we have learned a formalism for keeping track of all the number densities and all the ionization fractions and electron densities for all of these elements in a gas, right? And so why do we need to know that? Because when you go back and look at your spectra and you have, say, an absorption line, they say it's a, I always like to use, say, let's use an H-alpha line, okay, which we now know is a very complicated set of lines from a multiplet, but nonetheless it doesn't resolve out in our spectra, and we use the term averaged H-alpha constants. We have to know how the photons behave to a certain number density of neutral hydrogens in the first excited state. So the strength of that line depends upon what the number density along the line of sight is of that particular ijk. K equals 1 for hydrogen, J equals 1 for neutral, I equals 2 for first excited state. Okay, you have to model the gas balance in detail in order to know what that number density is. So really what happens with spectroscopy is you measure the line strength and then you model the gas to figure out, can I match that line strength? Can I match its width? Can I match its depth? In other words, its column density and its Doppler broadening. And also maybe I've got some other lines, some helium lines or some magnesium lines or some sodium 1 lines. So I have to know the number densities of those. If I turn up the temperature, I might make my lines match the broadness of my lines, but I might over-ionize sodium and make the line in my model be weaker than the actual line. Oh boy, what could be the problem? Well, maybe the radiation field is different. Change the radiation field. You see you have all these knobs to turn in your model. But what I've developed for you is a formalism for solving for those conditions if you wanted to model the gas. And you know, astronomy has evolved these days so that students are spending less time developing a PhD where they go to the telescope. They go, it takes them 2 years to collect their data and then they analyze their data and publish it. Those days are gone now. It seems like more people are doing something like Apogee and things like this, Sloan Digital Sky Survey, or and they're modeling large numbers of data. The other thing that's happening is you're using these pipelines, and you use these pipelines as black boxes. All right, you might be a very productive scientist using black boxes and using all these other data. And you might be able to make a great career out of it. But in the end, knowing the details up here, the physics, really allows you to understand the shortcomings of things. And sometimes what happens, and it happens more often than you think, you get handed a black box. You have to look under the hood because it turns out the black box doesn't account for something new that you want to learn that at the time they didn't design into the black box. So you have to understand the black box, and you have to understand maybe how to modify the black box. And that becomes more of a common type of thesis where how do you do your original contribution? You modify something else. You stand on the shoulders of something else. So you do have to know this stuff, even though the culture of astronomy is changing. At least I'm still old school enough to believe you should know this stuff. Okay. All right. So let's talk about something that's probably a little bit easier to, as Robert Heinlein said, grok. Okay. So there's a lot of mathematics involved in that. I just wanted to say, I'm not going to go through it, but I've thought about, well, it says homework problem question mark, but it's in your notes, isn't it?
Yeah.
Shoot. Next time I'll leave it out.
Okay.
Okay.
You can pretend like it's not there.
It can pretend it's like not there, and you could just copy it. So this is an example of what mu for a fully ionized gas would be, I believe. So basically, the definition of a fully ionized gas, if you want to know, is that all the ionization fractions are 0 except for the very last one. Okay. Let's say this is lithium. That's K equals 3. F13 equals 0. Okay. There is no neutral lithium. F23 equals 0. There is no singly ionized lithium. F233 is 0. There is no doubly ionized or triply ionized magnesium, or sorry, lithium, but F43 would be 1. All of the lithium has all of its electrons removed. That's how you would define a fully ionized gas. Does everybody follow me on that? Okay. So, then what you do is you start with that and you run that through the equations I gave you, and you use the definitions of x, y, and z that I gave you. How is that? Take the definitions of x, y, z, and when you get the fully ionized gas, you get this equation at the bottom, that mu is about 2 times 3x plus 1 half y plus 1, all to the inverse. And you can just show that by carrying out the equations with the only contributing term in this sum is when j equals k plus 1. So this just becomes f of k, k plus 1. And then you carry through the math, and you get this formula down here. So that's when somebody says they got mu of a fully ionized gas in their paper, that's what they're assuming mathematically. Okay, I just wanted to mention that. Okay. All right. So that lets us move on to the radiative processes now that will generate different excitation states, and the collisional and radiative processes that will generate different excitation states and generate different ionization states of your nuclei. Okay? And these are dependent upon your number densities, and they're dependent upon, the intensity of the radiation field. Okay? All right. So if you look at the bottom of page Radiative Processes, here, you can see the 3 that I've talked about, okay, and they have their inverse. This is basically ionization. You have a photon, this is excitation. You have a photon come in, you lift up in orbit, okay? You drop down to orbit, photon goes out, the inverse. You have a photon comes in, it ionizes the electron, okay? It now becomes a free electron and contributes to N sub E. Or you can have what's called recombination. A free electron comes in, becomes bound, therefore Ne is reduced, and now your ionization fraction for that element has changed because now you have another one with an extra electron on it. Okay, And then you have free, which we're not going to spend a great deal of time talking about, okay, until maybe the end of the course. The other process you also have is collisional excitation and collisional ionization. So instead of it being a photon, it could be another element, particularly electrons. Electrons come through. If they have enough kinetic energy, that can be distributed to ionizing the atom. This electron loses energy. This one gets added to the pool. The electron density goes up. Ionization fraction of that particular element goes up. Okay, so that the balance changes. And the other option is that you have de-excitations. Electron comes through and it actually impulses it and it de-excites. This one now has higher energy. Electron density doesn't change. That's collisional excitation, collisional de-excitation, and collisional ionization. Okay. So in a gas that's in thermal equilibrium, it turns out that Boltzmann and then a guy named Saha were able to write down some nice simple equations for how you can solve for the excitation, the densities of the excitation states and the densities of the ionization stages. Okay, so that's what we want to talk about a little bit. And under those conditions, okay, we have something called detailed balancing. That has to be happening. This means that the photon field, again, is specified by a single parameter, the temperature, and the kinetic energies and the pressures and all of that are described by a single property, basically the temperature. Okay. Then the density constrains how thick the gas is, and then these rates of these processes will depend upon densities and densities squared. But in the end, what we're going to talk about are conditions, very special conditions, please. When you want to calculate ionization fractions in a gas, do not use the Saha equation unless you are assuming thermal equilibrium. Do not use the Boltzmann equation, which lets you get the excitation values, unless you are in thermal equilibrium. Okay? There is a whole another set of ways that you have to solve the ionization conditions and the detailed balancing in gas where the photon field is not in equilibrium with the particle field. Okay? You have to treat them as uncoupled. But when you can couple them, you get out these very simple equilibrium relationships. Okay? I think you guys are so saturated you can't even see straight. I think you're all cross-eyed today.
Just another anybody refer to the Saha equation as a simple expression.
Compared to the full way of solving a gas, where you've decoupled the radiation field, yeah. If you can write it in a closed form, it's simple. Okay, so what I want to do when we come back on Tuesday is I'm going to give you a homework assignment to let you exercise these equations to transfer between these things. And when we come back, I'm going to then tell you about the Boltzmann relationship, which gives you the relative excitation states. I'm going to tell you about the Saha, maybe you've seen these before, that gives you the relative ionization stages. Once I've given you that, here's the important thing. I'm going to teach you something called the recursive Saha method. At least I call it the recursive Saha method. And that's how you calculate the ionization fractions. So then you will be fully armed to solve for the equilibrium conditions of a gas once I arm you with the recursive Saha. I know you're not going to get any sleep this weekend. Okay, in the meantime, I'm supposed to hand you some problems to do, to be due by next Tuesday. So I will have those to you in time for the weekend, and if you need to hand them in on Tuesday afternoon, I'm going to be okay with that. but in class would be the most awesome. And I'll try not to make it too, crazy. What I really want to do is I just want to exercise, having you exercise to review everything that we've talked about. So I'm going to hit on what I think are important points and just make sure, kind of like a glorified homework assignment in terms of breadth. Okay? All right. Okay. Thanks for your patience and